Okay, hello, welcome back. We're going to go over the homework on properties of integration. So let's go, page 314, number 8, straight off the bat, just says, find the integral from -1 to 2 of 3x squared plus 2 dx. Okay, and there's really no way that we know of to do this problem right now, except by the so-called limit process. And alright, there are a couple different things that you might do here. Okay, well let's be kind of maybe smart about this or something. So the smart way to do this, I've never done this before with my students, but the thing that maybe you're just tempted to do anyway, so why don't we just do it, is to use properties of integration. And to use properties of integration, what that means is that we can, if we're taking the integral of the sum of two things, well that's all an integral is, it's an infinite sum. So let's split this up into the integral from -1 to 2 of 3x squared plus the integral from -1 to 2 of 2. And perhaps now we can use a property of integration, and the property of integration is that the integral of a constant function is just that constant times the width of the interval. And of course that makes total sense, because if we're integrating from -1 to 2 of the 2 function, then to the extent that this is just the area under the curve, then this is just a 3 by 2 rectangle, so this is just going to be 6. So here we get 6, and here, well, I'll use one more property of integration, which is that the integral from -1 to 2 of 3x squared is just 3 times the integral from -1 to 2 of x squared. Okay, and that's kind of nice because it leaves us with just one simple thing to do, which is this: find the integral from -1 to 2 of x squared. Okay, and now, this is something we've almost done before, but not quite. So, well, now maybe we'll just do it the slow way, where we don't have deep thoughts, we just do it. So what is the integral from -1 to 2 of x squared? I'm going to find this number, and then I'm going to multiply the number by 3 and then add 6, and I'll have my answer. Okay, well, let me make a picture to aid in understanding. Yeah. So what does this look like? Well, when I plug in -1, I get 1, of course, and when I plug in 2, I get 4. So we have a function which looks something like that, a curve which looks something like that, and the goal is to find the area under this curve, and so this is just the stuff that we were doing last week and earlier this week. That's just what an integral is. It's finding the area under the curve, and we've given a precise definition of integral, which says divide the integral up into subintervals, and in this case, if I'm going to use n subintervals, then since the width of the entire interval is 3, then delta x is going to be 3 over n, and then I will just begin sort of doing that, right? I'm going to use rm, because why not? So I have one subinterval, another one, another one, another one, etc. And what are all these points? Well, that's just -1 plus 3 over n. That's -1 plus 2 times 3 over n, etc., etc. -1 plus 3 times 3 over n. And by the time I get to the ith rectangle, is going to have x coordinate -1 plus I times 3 over n. And I know I'm doing it correctly because by the time I get to the last rectangle, it will be -1 plus n times now. I've moved over by 3 over n, and so that just becomes 2, which is what it's supposed to be. Alright, so if I have that kind of understanding here, well then I can tell you what this answer is going to be. It's going to be the limit, as n goes to infinity, of the sum from I equals 1 to n, and I'm adding up n things. What are the n things I'm adding up? I'm adding up essentially the area of n rectangles. Since this function's positive, I can say it that way. And what is the height of the nth rectangle? It's just what happens when I plug -1 plus I times 3 over n, which is the right endpoint of the ith subinterval, into the function. That's the height of the ith rectangle, and the width of the ith rectangle is delta x 3 over n. Okay, so this is quite abstract and sort of theoretical and complex, but once you do it a couple times, maybe it's not so hard. Okay, so now what can I do? I can factor this 3 over n out of the summation. I can just do out this algebra, which gives me 9 over n squared I squared minus 6 over n I plus 1. I think I did that correctly. And now I'm going to split that sum. I'm going to try to squeeze this in here. I'm going to try to split that summation up into 3 smaller summations. The sum from I equals 1 to n of, now I get 27 over n cubed out here, I squared, minus 18 over n squared times the sum from I equals 1 to n of I, plus 3 over n times the sum from I equals n to I equals 1 to n of 1. So I just applied properties of sigma notation to split that up into 3 smaller sigmas, and here we get 27 over n cubed times, I now just know this formula. It's n plus 1, 2n plus 1 over 6. I know this formula as well. It's n plus 1 over 2. And here I'm just adding adding 1 n times, so that just becomes n. Okay, so still committed to squeezing this in here. What do I get? I get 2n squared plus 3n plus 1 over 6n squared. Sorry, and then there's also not 6n squared. Let's see, if I take a 3 out of the top and the bottom, I get 9 halves. So sort of, let's think of it like that. 9 halves times that, minus 9 times n plus 1 over n, and then plus 3. Okay, and as n goes to, just double checking, do everything, as n goes to infinity, this entire rational expression is going to 2, and that entire rational expression is going to 1, and so I think the whole answer to this problem is 3. Could that be true? Give me 1 second. I guess that just is true. 2, 4, 8, and 1. No, I thought, yeah. So the answer to this whole problem is just 3. Okay, and that means that when I now know that this is 3, I can just tell you that the overall answer to number 8 is 9 plus 6 is 15. Okay, so that was very fun. Is there some kind of other way to do this? Well, here I simplified my work. So I could have just immediately applied the limit process to the entire function, 3x squared plus 2. It just means my numbers would have been a lot bigger. Hopefully if you did that, I bet that's what most of you did, because that's what I've sort of instructed you to do via the videos, and that's what they do in the book. And that's what I've done, frankly, every other year. It just kind of went totally mindless from the beginning. Then hopefully you just also get 3, but it was the algebra and arithmetic was a little bit bigger. Here I've sort of done a little bit of thinking and understanding first by using a property of integration to split these up into 2 different integrals and factoring out the 3. So now I have just only like the x squared function to work with. It's possible to even be smarter about this and do even less work if you're willing to be kind of casual and think sort of geometrically. There's a couple of things we know. We know, because we just did it already, that the integral from 0 to 1 of x squared is 1/3. Okay, and if we just know this and feel it deep in our hearts, then, and I personally do feel it deep in my heart, then what this is telling me somehow is that the fundamental, like, parabola shape fills up 1/3 of the 1 by 1 box, near the origin. So if this whole thing has area 1, because it's just a unit square, then the parabola y equals x squared fills up 1/3 of it. Okay, if you just fundamentally believe that, then when it comes to doing this problem, the integral from -1 to 2 of x squared, I might further, now I really am going to run, well, let me do this. Let me erase this, because I think I proved my point that one can do this with careful algebra, but now I'm trying to maybe avoid that in the future. Okay, so if I accept this fundamental shape, then when it came to concluding that this integral from -1 to 2 of x squared was 3, that's what I wanted or when it came to determining what the integral from -1 to 2 of x squared is, another thing I could have done was to split this up into the integral from -1 to 0 of x squared plus the integral from 0 to 2. Okay, so why would I want to do that? Well, because, you know, this integral is, because this function is even, this is just the same as the integral from 0 to 1. Okay, make a picture if you want to understand that, but of course this function is even. And so, I now find myself in the situation where I already know that this is 1/3. So the only thing left really is to figure out what this is, and now I submit to you the following geometric argument. That the integral from 0 to 2 of x squared is just going to be a parabola of the same shape, I put that in quotes, of the integral from 0 to 1 of x squared. If you draw a picture of this, what do you find? So this is 1, this is 2, this is 4, and so what we get is this kind of shape. Okay, and this picture, not so great. This parabola shape that we wish to analyze, I claim, and I think this is intuitively true, although some argument is required to maybe convince skeptical people, that this shape which I want to know what its area is actually just still 1/3, but not 1/3 of this 1 by 1 square, instead 1/3 of this 2 by 4 rectangle. And since this rectangle has base 2 and height 4, then this area of this rectangle is 8, and this shape, this parabola, starting at 0, 0 and going to 2, 4, takes up 1/3 of that rectangle. And if that's true, then if this is 1/3, this shape is going to be 1/3 of 8, otherwise known as 8/3. And therefore, I conclude that this integral is 3, which is what I got doing a more algebraic process. So fundamentally, if you just kind of learn these shapes on the interval 0, 1, by doing out the calculus and the algebra and taking the limits, you almost sort of don't have to do it again if you kind of believe this argument. And so actually this entire problem could be done by splitting up this interval into two, applying a property of integration that says the interval of a constant is just the constant times the width, factoring out coefficients, getting it down to some kind of thing here where, you know, you sort of the negatives, if it's even or odd, every power function will be either even or odd, so you sort of adjust as needed. And then you just get these shapes, which are really just, depending on the function, here it's x squared, 1/3 of some enclosing rectangle. And everything leans upon already knowing this fact, which for this we did have to do it out the long way with limits. Okay, the last thing is, why should you believe this? Why should you believe that this shape is really just 1/3 of the rectangle? Well, now I want to, basically what I need to convince you is that these two shapes are the same. And by the same, I mean, this one is just this one stretched out by a factor of 2 and stretched vertically by a factor of 4. And I guess it just is, right? Because, why is that? Well, a calculus type argument can suffice to show this. I haven't actually thought this through, but when I go to the ith subinterval, which will happen at I over n, in the integral from 0 to 1 of x squared, then I get a little tiny rectangle. And what's the area of that little tiny rectangle? Well, the area of that little tiny rectangle is going to be the height, which is I over n squared, times the width, which is I over n. Sorry, 1 over n. And so, sure. And so I get I squared over n cubed. I think this is what I want to do. That is the area of the ith rectangle for this integral. For this integral, if I go to the ith rectangle, well, if once again I divide this up into n subintervals, then when I get to the ith subinterval in this integral, what is this coordinate? Well, now my delta x is my delta x is now what am I doing? Sorry, my delta x now is 2 over n because I have a width of 2, and therefore this point is just I times 2 over n because I've moved over by 2 over n I times. And when I plug, so now what's the area of the ith rectangle here? Well, it's going to be this 2i over n x value squared times the width of that rectangle, which is 2 over n. And so what you actually get is 8 times I squared over n cubed. And indeed, what I've just shown basically is that the ith rectangle under this integral has precisely 8 times the area as the ith rectangle under this integral. And so since there are n of these rectangles, indeed it really does have 8 times the area. And really there were two separate sort of arguments being made here, which is that the width of the ith rectangle is twice as much as this width, and the height of the ith rectangle is 4 times as much as the height of the ith rectangle in this shape. And putting those together is where we get the 8. And so you really can think of this shape as just a stretched out vertically by 4, stretched out horizontally by 2 version of this shape, which we know to be 1/3. All right. That is kind of awesome. I'm going to erase this now, sort of going a little bit off topic. not exactly going over the homework, but sort of giving a kind of a lesson. Okay, but I do think this is interesting, that if you want to take, say, the integral from 2 to 5 of x squared, that there is a kind of a shortcut that involves not doing a lot of work. And the shortcut is to say that this is really like the integral from 0 to 5 of x squared minus the integral from 0 to 2 of x squared. And again, this is a sort of an integral property that I can do this. And then just computing these by making a picture and thinking about it. What is the integral from 0 to 5 of x squared? Well, it's been stretched out 5 horizontally and stretched out 25 vertically. So this parabola, y equals x squared, lives inside this 5 by 25 rectangle and takes up 1/3 of it. We know. So this is going to be 1/3 of 125. And this integral from 0 to 2 of x squared, this is a repeat of what we just did, picture not to scale. This is going to be the area under the parabola y equals x squared inside of a 2 by 4 rectangle, and it's going to take up 1/3 of that. And if you just subtract those, then you're going to get an answer, which is whatever that is, 117 over 3. Okay, so that is just right. Oh, and I guess that reduces a little bit. 7, 8, 9. That's going to go in 33 and 6 times. This is just 39. Okay, so that's just a really fast way of doing integrals of polynomials, as long as you already know basic facts, like what the integral from 0 to 1 of x squared is. Okay, we now resume with the homework, going hopefully kind of just like fast now. So, yeah, that was 8. The rest of this homework involves a lot of sort of thinking and drawing pictures, but not algebra so much. So 30 says, what's the integral from negative a to a of a minus absolute value of x dx? This is kind of a strange problem maybe, but we can do it by just knowing things, I guess. What does absolute value x look like? Of course, it looks like this. So that means that negative absolute value of x looks like this. And then, and then if we want to move it up a, then here is my final picture, is that it's going to be sort of moved up a. But if it has slope -1, then we're going to have something that looks like that. So negative a, this is just what the curve a minus absolute value of x looks like, and you're meant to just draw it. And now that we realize what this question is asking is, what is the integral from negative a to a of this? Well, that's going to be just the area under this function, and that is just a triangle. And the very problem that integration was supposed to solve is to find the area under the curve, and we define the integral such that it does that. So this problem just reduces to, what's the area of that triangle? And we can just do this. This triangle has base 2a and height a, and so it's half of 2a squared, and so it's just a squared. Now, whew. Okay, boom, boom. 39 says, this is something kind of similar to what I was just doing before, but made a little bit mindless by the way the book has chosen to present it. But anyway, never mind. So here it asks you to do this integral, and it's kind of hinting at maybe what you should do. but they also just told you some facts. So sort of like fact 1, this is built into the problem, is that the integral from 2 to 4 of x cubed is 60. Okay, I'll just like take that, I guess. Fact 2 is that the integral from 2 to 4 of x is 6, and fact 3 is that the integral from 2 to 4 of dx, in other words 1, is just 2. Okay, so if I just know these 3 things somehow, then is there a way to do this problem quickly? Yeah, there is, right? I just apply integral properties. So split this up into 3 and factor things out. So this is just 1/2 the integral from 2 to 4 of x cubed minus 3 times the integral from 2 to 4 of x plus 2 times the integral from 2 to 4 of dx. And now I reach for these facts that were just handed to me. This is, I just trust them, 60. This is 6, and this is 2. And so we get 30 minus 18 is 12, plus 4 is 16. So they're, in some ways they're preparing us for the kind of logic that I did in that first problem, but not really taking it anywhere, I suppose, in my opinion. Okay, more. 41. Given the integral from 0 to 5 of f is 10, again, just abstract fact. Here it's kind of like the problem we just did, but now we don't even have polynomials, we just have some abstract unknown function. From this information alone, figure out some things. And the thing you have 4 things, it says 4 parts. Okay, A, what's the integral from 0 to 7? Okay, I might not write too much here because these were meant to be done sort of very, very quickly and easily, but okay, duh. What's the integral from 0 to 7? It's just the integral from 0 to 5 plus the integral from 5 to 7. So this is just 3 plus 10, this is just 13. Yeah, we're doing some math. Do you want to watch?
No, I did.
Okay, part B.
I know, I'll do some with you.
You want to do some math with me?
Yeah.
Okay, maybe. What's the integral from 5?
But I'll do some math with you.
Yeah, but I'm making a video.
Let's go downstairs, we can come do math with Papa later.
Okay, so, do you want to do some drawing, Ada?
Yeah, I do.
Okay, here you go. Okay.
Give me a mark.
Okay. Here is a purple marker for you. Woo! Okay, so what's the integral from 5 to 0? Well, I think what you should do here is just recognize that this is just the opposite of the integral from 0 to 5. By that integral property that we discussed in the previous video, this is 10, so this answer is just negative 10. That's all you were supposed to do there. Okay, part C. What's the integral from 5 to, what's the integral from 5 to 5? Dude, that's just 0. That's another fact which is seemingly silly and obviously true, but kind of maybe important or something. Finally, part D, what is the integral from 0 to 5 of 3f? And here we apply the integral property that this is just 3 times the integral from 0 to 5 of f, and that we were told is 10, so this whole thing is just 30. Okay, so hopefully these were like 2-second little problems. Okay, moving right through this, 45, this is quite interesting. 45 says use the table of values to find lower and upper estimates on the integral from 0 to 10. So I want to know the integral from 0 to 10 of f. Okay, assume that f is decreasing. F is decreasing. This is crucial. This brings together several ideas that we had in several different, maybe, lectures. Okay, let's just start. There's a table given. And I think this is interesting because, you know, calculus, you might think, is the study of, you know, continuous functions or something like that. And while that's kind of true, we often don't have the sort of access to continuous information the way we might want. And so we can still apply calculus principles to sort of discrete data, which is to say, suppose we have some physical, very strong, compelling reason to believe that our function is decreasing, but we don't know what the function is. In other words, we don't have an explicit rule for the function. But what do we have? We have some sort of data that was collected, and we would still like to reason about this function. For example, this function might indicate, might be velocity data, and then this integral will tell us the total distance traveled over the time interval 0, 10. And it won't be exact because we don't know exactly what the velocity is at every single second, but we have sufficient information that we can more or less do it. And so it's kind of, thank you, it's kind of like estimating, but estimating is in fact just as good as you can do. And now they ask, find upper and lower estimates. Because what I think we should do is make a picture, perhaps 2 pictures even. Oh, I made a strategic error. Let's see. I'm going to erase this error because I made a mistake. There's a little girl hanging out on screen, you may have noticed. Okay. Okay. So, yeah. Whew. Thanks, Ada. So when you plug in 0, oops. Okay. Yeah, when you plug in 0, you get 32. When you plug in 2, you get 24. When you plug in 4, you get... You want to contribute to the discussion? When you plug in 6, you get this negative 4. Okay. Okay, when you plug in 8, you get negative 20. And when you plug in 10, you get negative 36. Sorry, I'll come play with you in a few minutes. Okay, and while I'm at it, let me just very quickly draw this again. Oh man. She can come back up. This video is not that important. 2. She's screaming downstairs, I want to do more math. You can just let her back up, it's okay.